Okay, so part one, a few facts about measurement-based quantum computation. Okay, so measurement-based quantum computation starts with the state, the resource state, and the support of that state is a bunch of particles, say qubits. And to drive the computation, these qubits are being measured, like so. Okay, so let's just write that down. So this would be the resource state, that could be the cluster state, or anything we don't really need to know right now. And the other part are the measurements. So important about the resource state that it is entangled, and the measurements are local. Yeah. So that's basically it, and that's a universal scheme of quantum computation. There are a few more things to say about these measurements, so they will be very important in our discussion. So what I'm drawing here is a blob sphere, or the equator of a blob sphere. So imagine you're dealing with qubits. So this is, say, one measurement basis. Here you have another measurement basis, a basis of two states. And typically in a measurement-based quantum computation, or that's the model that we are looking at, for every qubit, there's going to be two choices for the measurement basis. And we call them q equals 1, or excuse me, q equals 0, and q equals 1. So two choices for the measurement basis at each qubit. Well, and then we also have two outcomes. So let's call them s equals 0 and s equals 1. And likewise for the other basis, s equals 0 and s equals 1. And so we have these labels q and s for every qubit. Q labels the basis, s labels the measurement outcomes. Okay. And so one thing that is very important for measurement-based quantum computation is the fact that every measurement outcome is random. And at that point you may ask, so then what's the worth of these random measurement outcomes? And the answer to this question is the value in having these measurement outcomes is in their correlations. So this is the important fact. So what we read out in measurement-based quantum computation are the correlation of these measurement outcomes. We are not interested in the measurement outcomes individually, only in their correlations. And because of this, measurement-based quantum computation needs classical site processing. And that classical site processing is very important for this lecture, and that's why I'm dwelling on it. So I need to provide you a little bit of technical background here. So let me specialize, because we don't need anything else here today, on one bit of outcome, and that let's call this outcome O. And this outcome O is related to the measurement outcomes. Well, that's what I already mentioned, and what I'm telling you now is the precise relation, because there is a precise mathematical relation for this. So, so we are going to have a sum over a bunch of measurement outcomes. So I are the labels for the qubits here. And so this will be from a certain set. Let's call it J. All right, and over the set J, which is a subset on our cluster, we are summing all the measurement outcomes. Each outcome, I forgot to say, or no, I have said it, is a number 0 or 1. So we are summing these outcomes modulo 2. That's an important equation for today, and therefore I'm giving it an equation number. So that's the first thing. This tells you how the computational output is related to the individual measurement outcomes. So that's what we are talking about here when we speak about correlations. Very simple relation. So the relation is not too linear. This is a very important point later on. But now suppose that what we are computing is a Boolean function. So we compute a Boolean function. Let's suppose this is our task. Yeah, and it goes from m bits to 1 bit of output. Okay, so now the question is, how do we get the input into the computation? So we have the input that's the input, m bits of it, and how do we get this into the computation? We get this into the computation by choosing the measurement basis, this one versus the other one. Okay, so there is a relation that connects the input to the choice of the measurement basis. So let us write that down as well. So this is going to be the other equation. So we have a label QL for every qubit site L. So let's write down this relation. Okay, let me explain what this is. So QL on the left-hand side is this choice of measurement basis for qubit number L, and it depends on a bunch of bits in the input. Yeah? So J here is from 1 to M. Yeah. So for every qubit L, there is such a set that decides which bits of input determine the choice of measurement basis at qubit L. And again, this relation is not too linear. I do not explain to you how these relations come about. Maybe you have watched a lecture on measurement-based quantum computation or read about it somewhere, then you'll know. If don't, please look it up. I cannot explain it here today. So let's just assume these relations as given, but there's reasons for the relations being what they are. Let me just say that. Okay, so these relations will become very important in this lecture today, and what matters most is that they are linear.